So our speaker for this final speaker for this session is Haiyang Wang from UGA. Right. Okay. And he will talk about elliptic curves with potentially good supersingular reduction and the coefficients of the classical model.
Thanks for the introduction and thanks for the opportunity to speak here. This talk is based on part of my thesis at UGA, supervised by Dino Lorenzini. We will use the following notation. OK is a Henselian discrete evaluation domain with field of fractions k. Pi is a uniformizer. V is a normalized evaluation on k. And little k is the residue field. We will assume that little k is algebraically closed. Let E over k be an elliptic curve given by this minimal Weierstrass equation. We can define E tilde over little k be the curve defined by the above equation modulo pi. If E tilde over little k is an elliptic curve, respectively nodal curve, cuspidal curve, we say that E over k has good, respectively multiplicative additive reduction. Let me recall the semi-stable reduction theorem for elliptic curves. Let E over k be an elliptic curve, then there exists a minimal finite extension L over k such that the base change EL over L has either good or multiplicative reduction. If EL over L has good, respectively multiplicative reduction, we say that E over k has potentially good, respectively multiplicative reduction. Another way of constructing a reduction elliptic curve is through the minimal regular model. Let E over k be an elliptic curve. A model of E over k is a scheme curly E over OK whose spatial fiber, whose generic fiber is isomorphic to E over k. Here is a picture of curly E over spec OK. In the picture of curly E, you see that there is a generic fiber which is isomorphic to E over k. There is also a spatial fiber that defines a reduction of E over k. If curly E over OK is proper, regular, and minimal in the sense that there is no negative or rational curve, we call curly E over OK a minimal regular model. Kodaira and Neuron classified all the possible spatial fibers of minimal regular models of elliptic curves. The types of the spatial fiber called the Kodaira type are denoted by the following symbol. There is I0. This corresponds to a good reduction. There are IN with n greater than 0. They happen in the case of multiplicative reduction. And there are the rest. These occur in the case of additive reduction. Here are the pictures of the spatial fibers of the Kodaira type IN and IN star. In the picture, each of the line represent a copy of P1. Our guiding question is the following. Given an elliptic curve E over k with additive reduction, its potential reduction type and the minimal extension L over k to semi-stability, is it possible to determine the Kodaira type that E over k can have? Let me first recall the case when the characteristic of the residue field is not true. In this case, it's relatively simpler. Assume that the characteristic of little k is not true. Let E over k be an elliptic curve with additive reduction over OK. Then E over k has potentially a multiplicative reduction if and only if over OK E has the reduction type IN star with n greater than 0. In other words, E over k has potentially good reduction if and only if over OK the reduction type is 1 in this finite list. However, when the characteristic of little k is true, the above theorem is not true. And actually, it's easy to find an example of elliptic curve E over k with Kodaira type IN star with n greater than 0 and potentially a good reduction. From now on, we will assume that the characteristic of the residue field is true. There are three cases to consider. Assume that E over K has additive reduction, then EL over L can have a multiplicative reduction, good ordinary reduction, or a good supersingular reduction. Here, ordinary means that the endomorphism ring of the elliptic curve is order in an imaginary quadratic field, and supersingular means that the endomorphism ring is order in a quaternion algebra. In case 1 and 2, we always have that L over K is quadratic. But in case 3, the Galois group L over K embeds into SL to F3, but the Galois group can be as big as the 4 group, which has order 24. Before I state the results that address the previous question, we will need the following invariant. Let H be the Galois group of L over K, and let HIs be the higher ramification groups of L over K. The invariant SL over K can be defined by this equation. Note that the right-hand side of the equation is a valuation of the difference of the extension OL over OK. If L over K is quadratic, then the extension L over K is widely ramified. This invariant SL over K is greater than 0, since here we are assuming that K is algebraically closed to characteristic 2. The invariant SL over K mirrors the wide ramification of the extension L over K. Case 1 and 2 of the previous question were addressed by my advisor, Dino Lorenzini. Let OK be as before, and let E over K be an elliptic curve with additive reduction and potentially multiplicative reduction. Then there exists a quadratic extension L over K such that the base change EL over L has a multiplicative reduction. Let nu be the negative of the valuation of the J invariant of E. Then E over K has reduction type I star nu plus 4S L over K. When E over K has additive reduction and potentially good ordinary reduction, then still there exists a quadratic extension L over K such that the base change has good reduction, and the reduction type of E over K is I star for SL over K. Notice that the formula for computing the indices here agree, since when E over K has potentially good ordinary reduction, then the valuation of the J invariant is equal to 0. When E over K has potentially good supersingular reduction, we proved the following result. Let E over K be an elliptic curve with additive reduction. Assume that there exists a quadratic extension L over K such that the base change EL over L has good supersingular reduction. Let J be the J invariant of E. Then the following is true. Assume that valuation of the J invariant is less than or equals to 4 SL over K minus 4. Then E over K has Kodaira type I star for SL over K minus VOJ with the index divisible by 4. Assume that VOJ is greater than 4 SL over K minus 4. Let F be the residue of 2 SL over K plus 3 modulo 6. Then E over K has reduction type 2, respectively I0 star, 2 star, if and only if F is equals to 1, respectively 3 or 5. In part A, the formula for computing the index agrees with the formula in cases 1 and 2. When OK has mixed characteristic and the valuation of 2 is small, we can further restrict the possible Kodaira type. Assume that OK has mixed characteristic 2. Let E over K be an elliptic curve with additive reduction and good supersingular reduction after quadratic extension. Assume that VO2 is 1. Then the reduction type of E over K can only be a 2 or 2 star. When the valuation of 2 is 2 or 3, we have a similar result. Conversely, in cases A, B, C, each of the reduction type indeed occur. when OK has an accurate characteristic, then we have a simpler statement. Assume that OK has accurate characteristic 2, then the following is true. Let m greater than 0 be an integer, then there exists a elliptic curve over K with reduction type I star for m and good supersingular reduction after a quadratic extension. And for the reduction type 2, I0 star 2 star, the analog statement hold. Now we have discussed a little bit about the Kodaira type. Follow-up question one might wonder is the following. Let E1 over K and E2 over K be elliptic curves with additive reduction. Let phi from E1 to E2 be an isogeny over K. Is there a relation between the Kodaira types of E1 and E2 over K? Let me first recall the following result of Tim Dokchitzer and Vladimir Dokchitzer. Let K be a finite extension of Q2, and let phi from E1 to E2 be an isogeny of elliptic curves over K of odd degree. Then the Kodaira type of E1 over K and E2 over K are the same. When the degree of the isogeny is 2, we proved the following. Let E1, E2 over K be elliptic curves. Assume that there exists two isogeny from E1 to E2. Assume that E1 and E2 over K have additive reduction and a good supersingular reduction after a quadratic extension, L over K. Then E1 over K and E2 over K have the same Kodaira type if and only if either the minimum of the valuation of JE1 and the valuation JE2 is greater than 4 SL over K minus 4, or the valuation of JE1 is equals to the valuation of JE2 is equals to 6 times VO2. To study the previous question, to study the question of Kodaira type under isogeny over any field, we were leading into the following conjecture, and we call it conjecture A. Let OK be as before, and let E1 over K and E2 over K be elliptic curves. Assume that there exists an isogeny of odd degree D from E1 to E2. Assume that the valuation of JE1 is greater than 0 and less than 15 VO2. Then the valuation of JE1 is equals to the valuation of JE2. An interesting consequence of conjecture A is the following. Let E1 and E2 be elliptic curves. Assume that there is an isogeny of odd degree D from E1 to E2. Assume that E1 and E2 have additive reduction and a good supersingular reduction after a quadratic extension. Then conjecture A implies that the reduction types of E1 and E2 over K are the same. We have proved that conjecture A is true for all odd D with D less than 400. Now I will discuss a conjecture. We call it conjecture B on modular polynomials that implies conjecture A. Conjecture B is usually easier to work with. Let L be a prime, and let phi L be the L's classical modular polynomial. Phi L has this shape. Let JLZ be the modular invariant function, and let CNs be the Fourier coefficients of JZ. By construction, phi L, JLZ, JLZ is equal to 0. Here is conjecture B. Let L be a prime, and let AMN be the coefficients of phi L. Assume that L plus 1 is greater than M plus N, and let R be L plus 1 minus M minus N. Then the following is true. If L is not equals to 2, then AMN is congruent to 0 modulo 2 to the 15 times R. If L is not equal to 3, then the congruence holds modulo 3 to the 3R. Moreover, if L is congruent to 1 modulo 3, then the congruence holds modulo 3 to the ceiling of 9 over 2 times R. If L is not equals to 5, then the congruence holds modulo 5 to the 3R. I will illustrate part A of conjecture B through the example of phi 3. Let V be the two-adic valuation Z. Let AMN be the coefficient of phi 3. Here I listed the valuation MN. The conjecture B predicts that the valuation of A10 should be greater than or equals to 45. And here we get exactly 45. And the conjecture predicts that this value should be greater than or equals 30. Here we get 31. So it's slightly bigger than the lower bound. This should be greater than or equals 30. We get 30. Greater than or equals to 15, we get 16. And greater than or equals to 15, we get 15. And for the indices that are not within the range of conjecture B, the valuations are usually small. We have verified that the conjecture B is true for all prime L less than 400 using the computation of the classical modular polynomials done by Andrew Sutherland. And the conjecture B has the following implication. If part A of conjecture B is true, then conjecture A is true. As a step towards a possible proof of conjecture B, we provide a closed formula for some coefficients of the modular polynomial. Recall that CNs are the Fourier coefficients of the J function. Let L be a prime and let M be greater than 0 and less than L. Then we represent AL, L minus M in terms of the Fourier coefficients of the J function in this closed formula. And we also have a formula for AL0. Note that in part A, if we take M equals to L, then we get this piece. But for AL0, there's an extra initial term. As far as I know, this formula was not in the literature. Using the formula, we are able to prove the following. Let L be a prime and let M greater than 0, less than or equals to L be an integer. And let L minus M be the coefficient of phi L. If M is congruent to 4 modulo 8, then L minus M is congruent to 0 modulo 2. And for M in these other congruencies classes, the congruence holds for higher power of 2. In particular, if AL0 is congruent to 0 modulo at least 2 to the cube. Using the formula, we are also able to derive the following 3 divisibility. If M is congruent to 1 modulo 3, then L minus M is congruent to 0 modulo 3. And if M is congruent to 2 modulo 3, then the congruence holds modulo 3 squared. In particular, AL0 is divisible by 3. Part C of the conjecture B for AL0 says that AL0 should be divisible by 5 cube in general. Recall that here is a formula for AL0, and C0 is equals to 744. So as you can see from in the formula, the initial term here is usually not divisible by 5. So we cannot get a 5 divisibility of AL0 from the formula directly. Our current goal is to obtain some 5 divisibility of AL0 by analyzing the right-hand side of this formula more closely. I will stop here, and thanks for listening.
So do you have some sort of intuition for why conjecture B lies conjecture A? Like obviously I don't expect you to like some intuition why that's the case.
To derive conjecture B from conjecture A, so we will use these properties that if there is an isogeny from E1 to E2 of degree L, then phi L of JE1, JE2 is equal to 0. By just this interpolation, so we can derive conjecture from conjecture B.
Okay, so that's all.
Yes. I haven't tried to get a closed formula for other modular polynomial besides the one we did. But I suppose that there is some similar closed formula for them. Yeah, but I don't know whether the method can directly give us the formula. Yes.
Let's say, again.